This is section 9.2 in Rosen on n-nary relations. The topics covered in this section. N-nary relations are very important for understanding how databases work. So n-nary relations are an extension of binary relations, only now we'll be using n sets, which can be any integer 2 or greater. For instance, if I had 3 sets, the Cartesian product A, B, and C would be the superset of a relation on those 3 sets. A 3-tuple, A, B, and C would be is what R would consist of. How might we use this? If we're going to relate names, GPAs, and majors in a database, 5 integers that have a particular property, the set of those. And then how about a database of airline, flight number, starting point, destination, departure time, and arrival time? That would be a 6-ary relation, if you will. All right, a little more formally, and if you have n sets, an n-ary relation is a subset of the Cartesian product of those sets. Those sets are called the domains, and the number of them is their degree, or is its degree. So the triples A, B, and C, each coming from the domain of the natural numbers, be a 3-ary relation. We're defining them as A less than B less than C. That's what defines the relation in this case. Here the domains are identical, but they need not be. Let's think again about the flight database. We have the airline, the flight number, the starting point, the destination, and the departure time. Here we only we're missing the arrival time from earlier discussion. But the point is that the domains are all different in this 5-ary relation, or relation of degree 5. So again, this n-ary relation is one of the ways that we can keep track of data in a database. So every entry in the relation is an n-tuple. We call that a record. And each of the coordinates in the n-tuple would be a field. Now, we have to be able to keep track of them because elements of sets are unique. So in order to find them, we typically have some kind of key. We call a primary key that is unique to every record or every n-tuple. No 2 n-tuples have the same entry. If you don't have a primary key or need another way of identifying it, you can have what is known as a composite key, such that it's a combination of domains that is unique to each n-tuple or record. Here I have a database of students, and the fields are name, ID, major, and GPA, and here are all the records. Which is the primary key? Well, one would expect that the ID number would be a primary key. No 2 students should have the same ID number. But is there a composite key that we can pick out of this? If we look at major, can't be a key because there are some duplications, some 2 math majors and 2 computer science majors. Student name at this point could be a primary key because no 2 names are the same. But if a new student comes in, another student with last name of Adams, then that could be a problem to use the student name as a key. Might be a little safer if we use the student name and the major as a composite key. Of course, if we had another computer science major come in with last name Ackerman, then that would no longer suffice as a composite key. GPA would probably not be a good candidate for a composite key because GPA is always changing and shifting. All right, we've got a few operations we want to discuss on relations of degree n. The first one is a selection operator, and you might think of this as just a data pull. You could say, oh, I want all the math majors, or I want all of the majors that have a GPA of greater than 3.5. And that would give you a subset of the records that meet that condition. So it's a data pull. Another operation is the projection. That is where we map the n-tuples from the set to another set where usually the record is smaller. In other words, we want to shrink the size of the record for the purpose of the projection. And we'll look at an example of that in a minute. Some fields may not be important for an application, and so we want to get rid of them. Or maybe some of the fields have sensitive information, and we want to project only the non-sensitive information. All right, so that's selection and projection. We have one more operator. It's called the join. And in the join operator, we have two different databases. Here, R and S, and they have their own degrees, could be different. But what they have is P fields that are the same. So if I want to join them, I need to identify the columns or the fields that are the same. And if there are P of them, I'm going to create a new database that has M plus N fields minus P because P is common between them. I don't want to double count. And so I would if R consists of the fields A1 through AM minus P and C1 through CP, S consists of C1 through P and B1 through N minus P, then the join will have these elements combined. All right, we'll take a look at an example of projection next. Here we have, first we're going to look at this P14, where the indices indicate which fields we have projected into a new, smaller database. And what am I projecting from? It's from my student database from earlier. I'm picking field 1 and field 4 and getting just student name and GPA to come up with a GPA database. So I'm not interested in this case in their major and their student ID. I just want to know what their name and their GPA is. Here's another example, P12, where I'm looking at enrollments and I want to project that into just the majors. I've got all my student names, their majors, and their courses that they're taking. That's a lot of extra information I don't really care about. I'm just going to project that using the first two columns. Now I have a nice small database with just the student names and their majors. That's a couple of examples of projection. You usually go from a larger database to a smaller database. For a join, here I have join 2. That means I've got two columns that are in common between two databases. What are those? I have a teaching assignments database and a class schedule database, and the common fields are department and course number. If I create a join of these two databases, I'll combine professor, department, course number, room, time to get a teaching schedule. Here's the department and course number are the common fields. Now I've joined professor with room and time. That allows me to create a teaching schedule. And that is a discussion of in-array relations and how they can be used to keep track of data of many, many fields.